Now I want to take a look at something called the limiting process, and in particular we want to take limits of course, functions. And with a limit, the first thing I would like to say about it is that with a limit, what you're looking for is how a function is behaving, what a function is equal to near a specific x value. The one thing we don't care about, the main thing that does not matter when you're taking the limit of a function, is what the function is equal to at that x value. All right, that's always the first thing people want to do, is evaluate the function at that particular number, but that's really the main thing that just doesn't matter. So for example, let's say we were looking at f of x equaling x squared minus x plus 2. All right, let's say that was the function in question. Now that's a quadratic, and it's going to have its vertex in first quadrant, and the x value of 2 is going to put you somewhere up here on the function. Now, since my hand-drawn graph is not going to be sufficient for what we're about to do, I'm going to let the calculator do all of our drawing calculations for us. I've already put x squared minus x plus 2 into the calculator. I'm going to go ahead and do a zoom standard and show you that, again, that is a parabola with its vertex pretty much sitting in first quadrant. I'll start off with using the trace option. And what I'm going to do, since I specifically said I want to know what this function is doing near 2, I'm going to start moving the x values closer to 2. So there I am at 1.9, and we see that the calculator is reading for a y value roughly 3.75 at that point. So as I head towards 2 from the left-hand direction, the y values are heading towards, right now they're at 3.75. Exactly what they're heading towards is what I'm interested in. But if I move a little bit further, the calculator skips over 2, jumps to 2.1, and I'm already at 4.39. So I've gone from 3.75 to 4.39, might as well call that 4.4. But the problem is, just using the trace option like this on the calculator does not allow you to get as close as you want. Because when you say, I want to know what the function does when I get close to a value, you mean infinitesimally close, not just near, but extremely, extremely infinitesimally close. So what I will do is jump to the table. I've got the calculator set so that I can choose my own x values. So again, since we're heading towards 2, I'm going to start out at 1.5. That puts me at 2.75. 1.6 would be 2.96. 1.7 puts me at 3.19. 1.8, 1.9. As you can see, it's gone over 3, and it's heading towards 3 3/4. So I need to move closer. I'm going to put 1.99. That gets me a little bit closer. 1.999 is even closer. 1.9999 is even closer. And it appears, at least to me, that the y values are getting pretty close to 4 as the x values get close to 2. Now I'm going to go ahead and do the exact thing that I said you're not supposed to do. I'm going to put in a 2. When I put in a 2, I get out a 4. So it looks like that function is heading towards 4 as you get close to 2. Now again, I see that in fact that at 2 it's actually equal to 4. But as I said at the very beginning, that's the one thing we really don't care about. That's not what matters. What matters is that as I get close to 2 on the x values, the y values get close to 4. How close? Well, honestly, so close that the calculator can't even tell the difference. I entered in a 1 followed by about 7 9s. Calculator can't tell. As a matter of fact, calculator, that is so close to 2 that the calculator can't tell the difference. And the y value, even though it's displaying a 4, that's a round off. So what's happening is as I get infinitesimally close to 2 on the left-hand side, on the x's, the y values are getting indistinguishable, infinitesimally close to 4. Now let's come in from the other side. We came in from the left, let's come in from the right. I went 2.1, 2.01, 2.001, 2.0001, and if I keep adding zeros, notice what's happening. Same thing's happening as you come in from the upper side of 2 as happened when you came in from the lower side of 2. When you get so close to 2 that the calculator can't tell the difference on the x, then the y gets so close to 4 that the calculator has a hard time telling the difference. This is the idea of limit, all right? And the idea is as I come in from the left on the x's, and as I come in from the right on the x's, the y values are coming up so close to 4 from the bottom and coming down so close to 4 from the top that it gets to a point that the calculator just can't tell the difference. And if you were to ask the question, how close to 4 does this function get? The answer would be it gets as close as you want it to get. You name any distance you want, and the function values will get that close to 4. All right? So therefore, we say that the limit, this is the notation and the language that's used, the limit as x approaches 2 of the x squared minus x plus 2 is equal to 4. And that in reality, and this may seem like a contradiction, this may seem odd, but the reality is that has nothing to do with the fact. It's got absolutely nothing to do with the fact that the function equals 4 when you plug in an x value of 2. At least for the moment, that is our approach. All that matters is as you get infinitesimally close to 2 on the x from either direction, you get infinitesimally close to 4 on the y from both directions. All right? In general, when this happens, we say the limit as x approaches a of f of x equals some limit L. And again, what that means is that as the x values get infinitesimally close to a, the function values get indistinguishable and infinitesimally close to L. Now, our first example was one where you could plug in the x value and it would give you a y value. And that is definitely not the way it's always going to work, right? We could look at the limit as x approaches 1 of x minus 1 over x squared minus 1. And notice that if you name your f of x to be the x minus 1 over the x squared minus 1, and you look at f of 1, you get 1 minus 1 over 1 squared minus 1, which is a 0 over 0. And we all know, at least you better know, that you can't divide by 0. So the function actually doesn't exist at the x value of 1, which is why I was so emphatic about the fact that the one thing we don't want to know, the one thing we don't really care about, is what the function equals at that x value. because here's an example of a function that doesn't even exist at that x value. But the limit, even though the function may not exist at a particular x value, the limit very well can. So we'll put that function into the calculator. Don't forget to use parentheses. I'm going to put an x minus 1 over an x squared minus 1 into the calculator. Go to our table. Get rid of some of these old values. And again, the first thing I'll show you is when you put in a 1, it doesn't exist. But that's not what matters. I don't care what's happening at 1. I care what's happening near 1. Let's come towards 1 from the left-hand side. I'll put in a 0.9, 0.99, 0.999, 0.9999, and so on. And it looks to me that if you get very, very close to 1 on the left-hand side, on the x's, the y values get very, 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 very close to 0.5, to the point at which, at this moment, the calculator can't even tell the difference. Okay, the calculator can't even tell the difference. That value does not actually equal 0.5. The calculator just can't tell that it doesn't equal 0.5 because it's that close. I put in a 1.1, 1.01, 1.001, 1.001, and a 1.0000001. Once again, you've gotten so close to 0.5 that the calculator can't tell the difference. All right, it cannot tell that that does not actually equal 0.5 at that x value. That's got round off error in it. It's why you're seeing that. But point is, it gets infinitesimally close. So therefore, the limit as x approaches 1 of x minus 1 over x squared minus 1, we would say equals the 0.5, or call it 1/2 if you want to. All right. Again, that is not because the function is equal to 0.5 at 1. It, in reality, if you were to graph it, what you would see, and you would have to look very closely. If you were to do quite a bit of zooming in, what you could eventually see, and it's very hard to pick out, but the function doesn't actually, again, as I said, doesn't actually exist at 1. And the calculator is going to probably lock up on us and not want to show it. But at the x value of 1, let's see if I can actually make it show it. No, it's not going to be able to do it. Calculator can't pull it off. At 1, there's literally a hole in that graph. You saw that graph coming down like so. There's a little hole right there at 1. And the calculator's having a really hard time showing it. It's choking up on that just a little bit because that's a lot of tough calculations for it to do. All right, again, this is a tough thing for people to accept, for people to get accustomed to. But we actually do not care what the function equals at a particular value. As a matter of fact, I could define a g of x as follows. I'm going to let g of x equal x minus 1 over x squared minus 1. All right, and that's what g of x is going to be if x isn't equal to 1. And I'm going to let it equal 2 if x equals 1. So I've just defined a brand new function. What would that function look like? It would look like this one. It would have a hole right here, but up here at 2, this piece of the definition puts a point up there. All right? So here's what we see. We see that g of 1 is equal to 2 by definition, and we see that the limit as x approaches 1 of g of x is equal to, guess what? 1/2. Right? Again, because what is the number one thing that I do not care about when I'm finding a limit? I don't care what the function actually equals, all right? I do not care that the actual function value is up here. I care that as I approach and get close from the left, and as I approach and get close from the right on the x-axis, what I care about is that on the y-axis, it's approaching 1/2. I don't care what the function equals. I don't care if the function's even defined at that point. When you ask the limit question, you only want to know what's it getting close to. Now, we've been doing these limits with the help of the calculator, which is not a bad way to get things started, but you can't always trust the calculator. You really can't, all right? There are plenty of examples where the calculator will give incorrect numbers, all right? The calculator can very well give you wrong answers, so you do have to be careful about that. There's an example here from an old book of mine where it wants to investigate the limit as x approaches 0 of sine of pi over x. Okay, and if you notice that plugging a 0 in here gives you division by 0, so this thing is undefined at 0. If you were to go on to graph it, if you were to go in here and plug some numbers in, what you might be tempted to guess is that that limit turns out to be 0. All right, calculator, as you plug numbers in here, calculator is going to lead you to believe, like if you plug in 0.001, 0.00001, it keeps giving you 0. So you might be led to believe that that limit does equal 0. But again, the calculator approach that we've been messing with here isn't rock solid. It is not the thing we want to depend upon for our limits. Because if you look at a good quality graph of sine of pi over x, then what you notice is that as you get close to 0 here, this thing begins to oscillate wildly, all right? And there is therefore no one numerical value that the thing approaches. Therefore, that limit doesn't actually exist. And it is entirely possible and quite common for limits to simply not exist. Not every limit question has a finite numerical answer, all right? Because we have what's known as both left hand and right hand limits. Let me draw a picture for you. Let's say I had a function that looked like this. Coming in from the left, it does this. From the right, it looks like that. Let's say that this x value corresponds to a 5. This y value is a 3, where this y value is a 4. All right? And again, the function I'm talking about is the f of, I'm going to call f of x. Now, if you were to ask the question, what is the limit of this f of x as x approaches 5? If that was your question, here's what you have to consider. If you just sort of imagine yourself traveling along this function coming in from the left, then you notice that as you travel from the left, you're heading towards, you're coming in towards an x value of 3, right? As you travel from the right, I'm sorry, I said x value, you're coming towards a y value of 3. As you travel from the right, you're coming towards a y value of 5, of 4. I keep on saying, let me try again. Let me back up. Let's try again. As you come towards 5 from the left, you're heading towards a y value of 3. As you come towards 5 from the right, you're heading towards a y value of 4. So this function actually has a limit that's different on the left than it is on the right. In other words, it's behaving differently on the left than it is on the right. Therefore, we write the limit as x approaches 5 from the left-hand side, which is what that little negative superscript means, of f of x. Again, as I'm coming in from the left, it's heading towards 3. The limit of f of x as x approaches 5 from the right, as you're coming in up here on the right-hand side, you're heading towards 4. All right, so a function can have a left-hand limit. It can have a right-hand limit. It can have what will come to be called an overall limit. It can have 1, 2, or 3 of these things. All right, and what we establish is that the limit as x approaches a of f of x equals some limit value, some number, if and only if, and the IFF with two, the two F's means if and only if, limit as x approaches a from the left of f of x is equal to L, and limit as x approaches a from the right of f of x is equal to L. So what we're saying here, there's more to this statement. Let's make sure we understand what's being said. For a limit to exist, for an overall limit to exist, here's what has to be true. All right, 3 things. Number 1, the left-hand limit has to exist. Number 2, the right-hand limit has to exist. And last of all, they have to equal the same thing. All right, the left-hand limit has to equal the right-hand limit. They both have to exist, and they have to be the same thing. All right, left-hand limit has to exist. Right-hand limit has to exist. They have to be the same thing. All right. Now, all of these limits thus far have been ones where the limit turned out to be, again, a finite number. L represents a numerical value. That is not always what happens. The limit does not always have to be a number. We can have situations in where the limit as x approaches a of f of x is actually equal to infinity. All right, that can happen. Prime example, if you let f of x equal 1 over x minus 1, then we'll just sort of demonstrate that on the calculator, then I'll show you by hand. You had 1 over x minus 1. All right, there's what the calculator has to say about it. All right, so here's what the calculator is trying to tell you. The calculator is saying it looks something like this with a 1 right here. What the calculator, see how this graph looks like mine, what the calculator is not telling you is that there is a vertical asymptote passing right through 1. Remember, vertical asymptote is a vertical line the function cannot touch, cannot cross. All right? So when a function has a limit value of infinity, what that means is as you're coming towards that x value, the function goes up infinitely. All right? On the other hand, if you were to say the limit as x approaches a of f of x was equal to negative infinity, that means it's going down. Okay? So for this particular function, we actually don't have exactly either one of these. If you looked at the limit of a 1 over x minus 1, as x approached 1 from the left, that would equal negative infinity. Because as you come in from this left-hand side, it's going down forever and without bound. The limit as x approaches 1 from the right of 1 over x minus 1 is positive infinity, because as you come from this side, it goes up forever and without bound. Therefore, the limit as x approaches 1, the overall limit of 1 over x minus 1 would simply not exist. The left-hand limit existed, the right-hand limit existed, but they did not match each other. Okay? So, what would be an example of something that does have a limit of infinity? What would that look like? Very simple function. If you look at g of x equal 1 over x squared, that's going to have a vertical asymptote that is the vertical axis, and it's going to look like that. So for this particular function, the limit as x approaches 0 from the right of 1 over x squared is infinity. The limit as x approaches 0 from the left of 1 over x squared is infinity. So since these limits match up in this way, since it's doing the same thing from both sides, the limit as x approaches 0 of 1 over x squared is also infinity. Now, I did say earlier in my definition, if the overall limit exists, as long as the left hand exists and the right hand exists. And by exist, I meant equal to actual finite numerical values. So this is the limits that yield infinities fall under a slightly different set of definitions. Make sure you read those. Again, the infinite limits fall under their own set of definitions. Because when it comes to a limit, there is a number of ways for a limit to fail to exist, right? Exhibit 1, here's one way for a limit to exist. The left hand may exist, the right hand may exist, but they don't equal each other. Therefore, your overall limit would not exist, all right? So if the left-hand limit exists and the right-hand limit exists and they're not the same, their overall limit does not exist. But all of these are also other ways that a limit can fail to exist. When you say a limit equals infinity, or when you say a limit equals negative infinity, you're not actually saying it exists, you're describing how it failed to exist. So this limit failed to exist because it did what we would call diverging to negative infinity. This limit failed to exist because it diverged to positive infinity. This limit failed to exist because the function was doing something different on the left than on the right. Okay, so there you have multiple examples of a way that a limit can fail to exist. Let me give you one more. Actually, not one I'm supposed to be doing right now, but I'm trying to sort of get you the full picture. Let's look at the sine wave. If you look at the sine wave, not at a particular numerical value, but just as you head out the curve, right? As you head out towards infinity. If you look at this function, you'll notice it never settles on any one particular behavior. It continues to fluctuate. And I'm going to hit this kind of lightly because I'm not supposed to talk about it yet. When a function doesn't settle into one particular behavior, that is another way that certain types of limits could fail to exist. All right, again, not something I'm supposed to be jumping into right now. That was a little bit of a foreshadowing of things to come. As far as limits are concerned, that is all we need to talk about for now. There's definitely going to be more to follow. We're going to do a lot with limits as time goes on, so just be prepared. They get used a lot in this course.